Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. An IT support manager spends 2 hours every morning manually scrolling through yesterday's tickets. Not because there aren't tools, because keyword search can't tell that server is slow and high CPU alert describe the same problem. Last video, we built the foundation of Retrieval Augmented Generation, or RAG. Today, we open the component that makes retrieval actually work: embeddings. By the end, you'll know exactly what they are, how to generate them, and where they plug into real IT automation. By the time this video ends, you'll have 3 concrete skills. Number 1, generate a dense vector for any support ticket text using a free model. Number 2, compute Cosine similarity to find how related 2 pieces of text really are. Number 3, place embeddings inside a RAG system and understand why they make automated ticket routing, knowledge-based search, and anomaly detection possible without a team of data scientists. Machines understand numbers, not words. If a user types, "The payment gateway is timing out," a rules-based system looks for those exact strings. It will never match a past ticket about checkout latency, even though they mean the same thing. Rule engines and SEQL-like queries fail because they have no concept of meaning, just character sequences. This semantic gap is a core reason why IT support still struggles to automate ticket routing at scale. Before embeddings, the standard approach was one-hot encoding. Take a tiny produce table: apple, orange, carrot with prices. One-hot creates a binary column for every possible word. Apple becomes a vector with a 1 in the first slot and zeros everywhere else. Orange gets a 1 in the second slot, carrot in the third. The vector length equals your entire vocabulary. For a support ticket system, the vocabulary can become enormous, producing massive, almost entirely empty vectors. This becomes a critical bottleneck for any natural language processing (ENLP) system that needs to handle real-world text. One-hot encoding has 2 fatal flaws that make it useless for any modern NLP system. First, the curse of dimensionality. As the vocabulary grows, so does the vector length, eating up RAM and grinding training to a halt. A dense embedding, on the other hand, packs meaning into a few hundred numbers instead of thousands or more, an order of magnitude compression. Second, and more damaging, one-hot vectors have no understanding of similarity. The distance between hot dog and shawarma is identical to the distance between hot dog and salad. The model can't learn that a shawarma is closer to a sandwich than a leafy bowl of greens. Let's lock in what we just covered. What 2 properties make embeddings superior to one-hot encoding for measuring semantic similarity? An embedding is a short, dense list of floating point numbers, typically a few hundred, that captures what a piece of text means. Think of it like GPS coordinates for meaning. In this vector space, king and queen cluster near each other, and man and woman are a predictable vector away. The model often learns to approximate relationships like king minus man plus woman, yielding something close to queen, though the result isn't perfect. Nobody told the model to do that. It learned the geometry of language by seeing millions of examples. The formal term for this is a dense continuous vector space. Every point is a semantic fingerprint. Word-level embeddings alone can't handle real sentences. The phrase "the server is down" versus "serverless is up" would confuse a word-based system because the individual word server gets the same vector regardless of context. That's where sentence embeddings step in. A popular free small model you can use is All-Mini LM L6 V2 on Hugging Face. It works by pooling all the word vectors into a single mean representation, so no matter how long your input is, the output is always a fixed size vector. One ticket, one vector. Check the model card for the exact output dimensionality. Here's what happens inside when you call model encode. Raw text enters the tokenizer, which splits it into subwords. For example, a word like unbelievable might be broken into un, believe, and able. Those tokens flow through a stack of transformer layers where self-attention figures out which tokens depend on each other, capturing context. The result is a vector for every token. Finally, a pooling step averages all those token vectors into one fixed-size embedding, 384 numbers for mini-LM. That fixed dimension is the key that lets you store and compare millions of these in a vector database without the index breaking. Dimensionality is only one part of the story. Smaller embedding models like All-Mini LM L6 V2 produce 384-dimensional vectors and are fast, efficient, and surprisingly accurate for many semantic search tasks. Larger models may generate 768, 1024, or even 1536 dimensional embeddings, giving them more capacity to capture subtle relationships. But more dimensions do not automatically mean better search results. Model architecture, training data, and the task you're solving often matter far more than vector size alone. Larger vectors also consume more storage and memory and increase indexing and query costs. The best embedding model isn't necessarily the biggest. It's the one that delivers the best balance of accuracy, speed, and cost for your specific workload. Regardless of the model you choose, semantic search typically compares vectors using Cosine Similarity, which focuses on how closely two vectors point in the same direction rather than how large they are. Let's build our first embedding application. Using the Sentence Transformers library, we load the free All-Mini LM L6 V2 model and encode two support tickets. The database connection was refused and cannot connect to the database. The model converts each sentence into a dense vector containing 384 floating point values. Although these numbers don't mean much individually, together they represent the semantic meaning of the sentence. Next, we calculate Cosine similarity between the two vectors. Because both tickets describe essentially the same problem using different wording, the similarity score will be high. Try changing the second sentence to something unrelated like reset user password and watch the similarity score drop dramatically. That's semantic search in action. Not matching words, but matching meaning. Quick recall. What metric did we just use to compare the two ticket embeddings? And what does it actually measure? There are several ways to compare vectors, but Cosine similarity has become the standard for semantic search. Imagine two arrows pointing in nearly the same direction. Even if one arrow is longer than the other, they still represent similar meaning because they're pointing toward the same concept. Cosine similarity measures that angle between vectors rather than simply measuring physical distance. Other metrics, such as Euclidean distance, consider both direction and magnitude and may be appropriate for certain models or datasets. However, most modern embedding models are trained with Cosine similarity in mind, making it the safest and most common choice for retrieval systems, recommendation engines, and RAG applications. Here's where embeddings become a business advantage. Imagine a customer reports, "Checkout keeps returning a 503 error." Another customer reports, "Payments fail every time I submit my order." A keyword search may never connect those two incidents because they use completely different words. An embedding model recognizes that both describe nearly the same underlying problem and retrieves the same troubleshooting documentation. At enterprise scale, that means fewer misrouted tickets, faster incident response, and better knowledge reuse. Behind the scenes, production vector databases achieve this speed using approximate nearest neighbor, or ANN, indexing. Instead of comparing every vector in the database one by one, ANN intelligently narrows the search to the most promising candidates, returning results that are extremely close to the best possible match while reducing search times from seconds to milliseconds. Once you've generated embeddings, you need somewhere to store and search them efficiently. That's the role of a vector database. Pinecone is a fully managed cloud service that lets you deploy production vector search without managing infrastructure. Weaviate is an open-source platform that combines vector search with rich filtering and GraphQL support. pgvector extends PostgreSQL with vector capabilities, making it an excellent option if your organization already relies on Postgres. Milvus is designed for extremely large-scale deployments where millions, or even billions, of vectors must be indexed efficiently. Each platform supports approximate nearest neighbor search, but they differ in scalability, operational complexity, filtering capabilities, pricing, and deployment options. Choosing the right one depends on your existing architecture, budget, and operational requirements. Embeddings are only as good as the text you feed them. That's why chunking is one of the most important parts of any RAG pipeline. Instead of embedding an entire document, split it into smaller sections that each focus on one idea. Include a small amount of overlap so important context isn't lost between chunks. Tools like LangChain's recursive character text splitter provide a good starting point because they try to split text at natural boundaries. Avoid embedding an entire 50-page manual into a single vector. It becomes too broad to retrieve accurately. Also avoid changing your chunking strategy after you've already indexed your document without rebuilding the embeddings, because inconsistent chunks can significantly reduce retrieval quality. Let's lock this in. Why is Cosine similarity preferred over Euclidean distance for semantic search? Cosine similarity measures the angle between vectors, capturing semantic direction regardless of magnitude, unlike Euclidean distance, which is affected by vector length. Let's recap before we move on. Why is cosine similarity preferred over Euclidean distance for semantic search? And why should you be careful with chunk sizes? Cosine similarity ignores vector length, focusing on angle, so it handles documents of varying lengths well. Using inconsistent chunk sizes can reduce search quality by creating mismatched vectors. Keep those points in mind when designing a vector DB. Never mix embedding models. It is the fastest way to break your search. If you indexed your knowledge base with one model and then query with another, the vectors live in completely different spaces. They don't align, and your similarity scores become noise. Hard rule: lock in the exact model and dimensions in your vector database schema from day one. Same model at index time, same model at query time. Embeddings aren't limited to documents. They can also help analyze operational data. Imagine thousands of log messages arriving every minute from servers, applications, and network devices. Instead of relying only on keyword rules, each log message can be converted into an embedding that captures its meaning. Similar log events naturally cluster together, making unusual messages stand out as semantic outliers. This doesn't replace traditional monitoring, metrics, or alert rules, but it adds another powerful signal for detecting unexpected behavior. Combined with standard observability tools, embeddings can help surface emerging issues earlier and reduce the time engineers spend manually searching through massive log files. Embeddings aren't limited to text. Modern AI models can represent images, audio, code, and other data types inside a shared semantic space. Imagine an employee uploads a screenshot of an application error instead of typing a description. A multimodal embedding model converts both the screenshot and your documentation into compatible vectors, allowing the system to retrieve troubleshooting articles even when no text was entered by the user. Another approach is to extract text from the image using optical character recognition, or OCR, and then generate standard text embeddings for retrieval. These capabilities enable search experiences that work across multiple data types instead of relying solely on written text. Before we continue, it's important to avoid a common point of confusion. The embeddings we've discussed so far are semantic embeddings, vectors that represent the meaning of documents, tickets, or search queries. Large language models also use another type called positional embeddings, but they serve a completely different purpose. Positional embeddings help transformers understand the order of words within a sentence because transformers process many tokens simultaneously, rather than one after another. They are internal components of the language model and are not the vectors you store in a vector database. Although both are called embeddings, they solve entirely different problems. One of the most popular positional encoding techniques used in modern transformer models is rotary position embedding, commonly called ROPE. Instead of adding position numbers directly to token embeddings, ROPE mathematically rotates portions of each embedding according to its position within the sequence. This allows the model to naturally capture relative distances between words, making it easier to understand phrases, long conversations, and lengthy documents. ROPE has become widely adopted because it improves how transformers handle long context windows without significantly increasing computational cost. While this happens entirely inside the language model, it's one of the innovations that makes today's large language models far more capable than earlier generations. Let's lock this in. Why do large language models need positional embeddings? Transformers process tokens in parallel, so they rely on positional embeddings to understand word order. One approach is rotary position embedding, or ROPE. As a practical aside, storing 1,384-dimensional vectors is roughly 1.5 gigabytes, but actual sizes vary depending on the vector database and compression choices. Embedding storage grows quickly as your dataset expands. A 768-dimensional vector requires roughly twice the storage of a 384-dimensional vector, while a 1,536-dimensional vector requires about 4 times as much. Multiply that by millions of documents, tickets, or log messages, and storage requirements increase rapidly. Beyond the vectors themselves, production systems must also store indexes, metadata, identifiers, and replicas for reliability, so the actual database size is larger than the raw vectors alone. Managed vector databases charge based on storage, indexing, and query volume, while self-hosted solutions trade subscription costs for operational overhead. Understanding these trade-offs early helps you design systems that remain both scalable and cost-effective. Generating embeddings no longer requires expensive GPUs or machine learning expertise. Most major cloud providers now offer managed embedding APIs that convert text into vectors with a simple API call. OpenAI, Azure, OpenAI Service, Google Vertex AI, Amazon Bedrock, and Cloudflare Workers AI all provide embedding capabilities for different deployment scenarios. When selecting a provider, don't compare only price. Also consider latency, regional availability, data residency requirements, security, model quality, version compatibility, and integration with your existing architecture. For many organizations, embedding generation has become a standard infrastructure service, much like databases or object storage. Here's a portfolio project that demonstrates real AI engineering skills. Export several hundred historical support tickets from Jira or ServiceNow. Generate embeddings for every ticket using a sentence transformers model. Next, apply k-means, clustering to group semantically similar tickets together. Experiment with different numbers of clusters until meaningful categories begin to emerge. Then inspect the tickets closest to each cluster's center to identify recurring issues, duplicate requests, or undocumented problem categories. Finally, build automatic tagging or routing rules based on those clusters. This project showcases semantic search, machine learning, data analysis, and practical automation. Exactly the kind of work employers increasingly look for in AI and platform engineering roles. Quick check. How can you cluster support tickets using embeddings in a single weekend? Export recent ticket descriptions, embed them with sentence transformers, run k-means clustering, inspect centroids, and create auto-tagging rules. 3 things to walk away with. 1. Embeddings convert text into numbers that capture meaning, something one-hot encoding could never do. 2. You can generate and compare those vectors with a free Python library under 10 lines of code. 3. They're the retrieval engine behind RAG, the secret that makes generative AI actually useful in production. That's the missing piece. Now you've got it. You've got the vectors. Now build something. Here's a weekend project. Install sentence transformers, embed 100 tickets from your help desk, and rank them by Cosine Similarity. Share the result on LinkedIn. That's a real portfolio piece. Then scale it, spin up a Pinecone index and take it live. The quick start link is in the description. Coming soon, we'll tackle RAG architecture and production deployment. Subscribe and hit the bell so you don't miss it. Coming soon. More in this series. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.